Okay, hello everyone. Doing a little update on my project, which you can see here. Doing an update now for reasons that I'll go through in a second. So this, as people may know, is a coding environment for. Well, it's a coding environment. Let's put it that way. So it's based primarily. It's a visual kind of approach. So up here I've got 3 orthogonal basis vectors. You can see them visualized as arrows. I can grab at any time, and that changes these arrows, and so it changes absolutely everything else in the scene. So those are ordinary vectors. You can see an example down here, but I can do things like I can type the letter O, and that gives me the orange vector, and then I can add a blue vector, and that gives us, as you can see here, the addition of those 2 vectors, and it's visualized in this output column here. That's now, you've just seen one of the bugs that's in there. This has just changed color, but now it's the case that I can do purple, orange, space, and wow, is it purple orange? Not purple orange, but purple red. Yeah. So there it is again. This is now a variable that's in scope. So it's a functional language. So if there's a line that doesn't have anything in the output column, then that line hasn't changed the variables that are available to the programmer in any way. So you can think of this as this output column here is kind of implicitly saying, these are new variables that have been created by whatever's on this line. As you can see, I was just using this it's an automatic variable naming system. Everything gets a color. The only things that aren't colored right now are the zeros, which are, that's on my to-do list. But so up here we've got blue, gray, orange. So that corresponds to the letter B, the letter G, and the letter O. It has 7 colors in total. Blue, orange, grey, red, yellow, white, purple. That's 7. It has every combination of those. I say every combination of those. It goes up to 3 colors right now, which means that you only get 63 possible variable names, which is not very many. But it might be enough to, make a nice educational visualization or make a nice shader, potentially. I'm not saying people should be satisfied with 63 variables, but that's the approach that I'm using with this thing, certainly for now. Being able to infer the name of something just by looking at it is, to me, very useful. There's more that I could say about this, but it might go, so best to move on. By the way, color blindness is a problem for those particular colors that I've selected. I'm hoping that I can find a more refined, more color blindness friendly set of colors, but those will do for now. Okay. So these are vectors. Another thing that you can have in this program is a scalar. So yellow is currently a scalar. Do you know what? I'm just going to change something terribly. Sorry. Goodness gracious me. What's going on? So, I was just, that's just something I need to fix there. So, we can have the yellow one. This is a scalar. It's a quite problematic representation of a scalar. You can't really tell whether it's positive or negative. And it has an implicit direction, which it shouldn't do. Scalars do not have direction, they only have magnitude. But I'm trying to think of a way of making it a bit more agnostic to the frame that you've got, to the angle from which you're looking at it. Actually, what you just saw, the bug that you just saw there was me experimenting with making it making it not, at least not rotate when you do this. So in this one, this is where these things are declared. So these guys up here are your orthogonal basis vectors. There's no changing them. These ones are free parameters, and so I can change this scalar. And as you can see, so like if you look over here, oh dear, oh dear. No idea what's going on there. This thing is as buggy as hell, by the way. I'm showing. Yeah, I'll tell you why I'm showing you this now. But in this rather buggy state. But yeah, so that's me changing the magnitude of a scalar. It's changing here. It's changing here. It's changing the results of certain calculations we're doing with it. Here we've got a free vector. I can do this. Changes the results down over here as well. This white thing is only going to be familiar to people who have a little bit of familiarity with geometric algebra. Geometric algebra is what sort of this project has been about to a very large extent. With this bivector has a magnitude as well, and I can change its magnitude by doing that. So let me use that bivector in something. So we have blue times by white. Yeah, here we go. So if you apply this white bivector to this blue vector, you get this vector that's pointing up here. And if I change this bivector, you can see that it's having an impact on that vector in the column over there. Although you can't see it changing that much because I normalize these things when I put them in their little windows. But hey, it is changing, I promise. Okay. Here we have a combination of a scalar and a bivector. A scalar and a bivector together make a rotor. Well, it has various names. You might call it a rotor, you might call it a spinner, you might call it a complex number, you might even call it a quaternion. In some strong sense, all of these things are the same thing, at least in this context. Bivector added to a scalar. With this particular thing, I can do this with a rotor. Let's just choose that name. With a rotor, you care much more about its you care about its direction, so to speak, much more than its magnitude. So I'm keeping the magnitude here the same. So the magnitude of this scalar and bivector together. What can you do with this? Well, those who are a little bit familiar with bivectors, but a bivector can apply a 90-degree rotation and a scaling to a vector. A rotor you can use to apply a orientation change to a vector. So if we take, let's say again, blue, and we multiply it by blue-orange. Oh, no, we shouldn't do that yet. Oh, yeah, let's do that. Sorry, blue-orange times by blue. That is it's a non-commutative operation. What I've got here, this is multiply. And then what you kind of want to do is we're going to say, I call it the reverse of that blue-orange. So reverse means you flip the bivector part. If we then and that outputs another rotor, but it's a rotor that's very clearly linked to the original rotor. And then we do blue multiplied by orange red. No, not orange red. Orange red, white red. Maybe this color naming system is not such a great idea after all. But yeah, so here it is. So keep looking at this blue-purple vector here. If I now go up here and I change this thing, you can see that it is changing the direction of that thing. Yeah, so may seem a little bit. It may seem like this is a rather quite a few lines of code to just to rotate a vector, but it is there for a reason. This is what most 3D engines do under the hood when you ask to rotate a vector. And the purpose of this program, to a large extent, is to show people what's going on under the hood of many game engines, 3D graphics things. Okay. Another thing that you can do with a bivector and a rotor that's kind of interesting with this program. If I do exponential, I can do exponential of yellow, and since yellow is a scalar, it just gives you this other scalar. I can also do the exponential of our bivector. So the exponential of a bivector is a rotor, in the same way that if the exponential of an imaginary number is a complex number. Yes. And that's quite useful. So it becomes, there's a way of controlling this rotor down here is to change the magnitude of this bivector here. Yeah. That's one thing that's kind of nice about, if you only ever think about quaternions and you never think about bivectors, it's hard to understand this nice relationship with the exponential function. Yeah, so that's why that's why. Yeah, that's an argument for geometric algebra. You can read a lot about it elsewhere. Yeah, that's the bulk of what you can do in this program. So, if you want to make a new vector, there you go. There's a new free parameter. Oh dear, that's incredibly buggy. It is not editing that new vector. It is editing, for some reason, the blue vector. That's probably because it's the first one declared in the program. Oh well. But okay, let's be super careful with this. Make a new vector. Are you going to behave? Okay. Yeah, that's how you create a new free variable. I'm thinking about binding that to the keyboard, like press the number 1 and it makes a new vector, because a vector is a grade 1 element. Press 0, that makes a new scalar, because that's a grade 0 element. In principle, at least, you can make a rotor. That might be buggy. Let's see. Oh, there, that works. Cool. Got curve here. That is buggy. And if but once upon a time, I was able to click this and draw a curve through space with the mouse, and the idea is that will become a function in your program. A function that maps, let's say, scalar, so like the time axis over the course of you doing this with your hand, to the position where your mouse was at that time. Yes, I have lofty ambitions for this program that you can see in another presentation that I've uploaded. However, the reason that I'm doing this now is because I've maybe had a little bit of a crisis of faith about how powerful my visualizations here are. So if I write exp, it becomes this cone thing. The reason it's a cone, so if I look at it that way, you can see that that's an exponential curve. It's this way as well because essentially the complex numbers, exponentiating complex numbers, gives you a circle in some strong sense. And I want to think of I want to be as visual as possible, right? Like, even the plus sign and the multiply sign, I sometimes, at points I've been like, oh, do I have to have a symbol there? Symbols suck, right? But how far can I go with this system? Well, I can probably go quite far. I can probably make it so that, I can take most of the equations in a random physics textbook and I can turn those into visualizations in a very, very easy way just by writing them in the system, which I appreciate, which I like. But essentially, I talked this yesterday morning to a cool guy, John Selig, who's a major name in geometric algebra, and he was like, geometric algebra is good, but sometimes you want to change representations quite a lot. Certainly, you want to change from one kind of way of looking at your abstract objects to another way of looking at them. And when I say way of looking at them, in his case, he's a very algebraic kind of guy. He's not just talking about a different way of visualizing them. He means changing the algebra using matrices instead of quaternions and that kind of thing. I think that there are enough interesting ideas in this program, and there's even quite a lot of things in it that that aren't very geometric algebra at all. So, here's a torus function. Just I felt like making that as a function. There's enough ideas that I've got for this program that I really think that I can turn it into something that I can use to at least make some interesting videos and maybe a shader coding thing. That'll be nice and maybe integrated into other programs. And it's definitely the case that geometric algebra is really cool, I still think. But I'm going to shift the focus of this project away from geometric algebra, probably to a large extent. And so I wanted to make this video before I tear up a lot of these things and replace them with something else. Really, what you ideally want is a system that you can bootstrap and make it so that you can code your own visualizations within the system to go inside of these squares. That kind of thing. That's all, I guess. Hope you enjoyed that. See you later. Very interested to hear feedback.